Okay, so the next speaker of this morning session will be Professor Walter Lamberti from the University FAMAF of Córdoba, Argentina, and he will speak about a Procustes approach to distances between quantum states. Please, Walter, go on.
Okay, thank you very much. I would like to start saying that 10 years of this event is a very effort from several young people, Federico, Martin, Olympia, and several others. I will like to emphasize the effort to keep this meeting every year. Unfortunately, for the pandemic, we are not possible to share coffees and music and other events, but congratulations for everybody to keep this event going on. Okay, I will start the talk. The name Procustes came from a mythological character. The person is Procustes, that is known in mythological Greek as the master of deformation. Okay. Well, what have to do this with quantum mechanics? I will try to explain in the follow. Let's suppose we are going to a quantum shop and we need a quantum state rho. The person in charge of the quantum shop should take a state from the set of matrices known as density matrices, which has these properties. H sub n is the Hilbert space of our physical system. Rho are density operators, which are semi-definite positive operators with trace equal to 1. Okay. The problem is the following. We pay for the state we want, rho, but probably we get a state sigma. Then we will notice the difference. Is the quantum shop trying to scam us? In general, due to quantum foundation, we can be lenient with the quantum shop if rho and sigma are close, because in general, rho and sigma are not perfectly distinguishable. But what is the meaning of close? In the case of the desired state is pure, we only need to maximize the overlap this in order to distinguish between rho and sigma. But in general, if the state is a mixed one, we need to measure the distance between rho and sigma. The notion of distance have to do with the notion of a metric space. Yeah, in general, we can define a metric space as a topological space with a binary function d from the Cartesian products of x into the real number, the positive real number, with these three properties: positivity, symmetry, and the triangle inequality. In this case, the function d is called a metric. In some sense, this notion of metrics is non-local, because we are not assuming that x and y are close. Yeah. In general, we are working in a topological space where the notion of continuity or proximity are defined. Okay. So therefore, we mention this binary function as a non-local concept of metric. There are several examples of metrics or defined between quantum states. The most or the best known examples are the Hilbert-Smith, the trace distance, the Burris, and the Burris is particularly interesting because it's defined from the concept of fidelity, which is defined in this way. This quantity looks very complicated to evaluate, but from a result of JOSA, it is possible to evaluate the fidelity from the concept of purification. What is the purification? Is a map that allows to represent the states, the metric state, rho and sigma, as pure states. And it's very important to remark that the fidelity can be evaluated experimentally. In many experiments about teleportation or dense code, etc., this quantity can be experimentally evaluated. Well, what is necessary to have many distance between quantum states? There are some formal questions, for example, associated with the fact that the geometry of the space of the states depends on the metric used. When I talk about geometry, I want to say aspect like the geodesic or the curvature or many other geometrical properties. Even when you have the same space, the geometry properties depends on the metric you use on this space. This is a very important point. Another aspect that justifies to have many distance between quantum states are some practical aspects. For example, in this paper, this is a recent paper, the use of some particular distance can be evaluated from experimental setups. So it's not the same to evaluate experimentally one kind of distance between quantum states. I mean, if you use one kind of distance, probably you can evaluate experimentality, but if you use another, the experimental evaluation may be quite difficult. And this is another important result showing that some properties of a distance, for example, in this case, the Hilbert-Smith distance, depends on the kind of dynamics under study. You can prove that if the evolution is unitary, this distance have this property, but if the evolution is of Limblad kind, that result is not true. So there are several other motivation to study different kind of metrics, but I think these three are enough to mention, okay? Well, there is a connection between information and how you can distinguish two objects. For example, to distinguish a cat from a dog, you need to have different kind of information about each one of these animals. It seems similar, but if you know some particular aspect, you can distinguish in a better way both pets. So there is a connection between metrics and information theory. In that sense, this quantity that we were working a lot of time, known as the Jensen Shannon divergence, has its origin in information theory. Here, if we start from two probability distribution, P and Q, and we can evaluate the Shannon entropy of the mixture of both probability distribution, and we can evaluate this quantity, okay? In fact, this quantity have been used in several contexts, and therefore, we think it's a very relevant example of distance between probability distribution from the information theory. This divergence is a particular case of the Caesar family of divergence. A Caesar divergence is defined in this way, where we suppose that f is a convex function and at 1 is equal to 0. In the particular case of the Jensen-Shannon divergence, the function f is this one. There is an interesting connection between this divergence with the geometry of the simplex of discrete probability distribution. You can define the simplex of probability distribution as a manifold in the sense of the word manifold I'm talking about is in the sense of the differential geometry, and it is possible to the simplex P to give coordinates, and in this manifold there exists a particular metric known as the Fischer metric, which is represented in this way. but no, it's not important the details, but the important fact here is that we can provide a Riemannian structure on P from the Fischer metric. When you have a local metric, I emphasize local in order to distinguish with global metrics, because if you have these coefficients, you can evaluate the distance between two close points in the manifold P. So only in some particular case you can evaluate the distance between two separate points. When you know these coefficients, you can evaluate the notion of parallelisms in the manifold, the notion of geodesics, the curvature, and several other geometrical properties. Okay, so if you have a local metric, let's say the Riemannian manifold, you can evaluate this quantity. So if you want to evaluate the distance between 2 points, you can evaluate by using this curve or this one. In this case, when you use the line between P and Q, you evaluate the geodesic distance. In the case of the Fischer metric, it is possible to show that the geodesic distance is given by this expression. And in the context of quantum mechanics, I will back soon to this point, but in the context of quantum mechanics, this distance is known as the Wutter's metric. So it is possible to show that the Jensen-Shannon divergence can be written in terms of the coefficient of the Fischer metrics in this way, where this is the metrics and this is the connection associated with this metric. This is known as the Christoffel symbols that can be evaluated from the metric coefficients. And to higher order, the terms that here we can evaluate have to do with the curvature of the manifold. This is the relation is important because we can relate a global distance as the Jensen-Shannon divergence with local geometrical properties. A very important point of the Jensen-Shannon divergence is that its square root have been shown to be a real metric in the sense of the definition of a metric space. Yeah, that means the simplex P with the square root of the Jensen-Shannon divergence is a metric space in this sense. Okay. One aspect, and one is an important aspect, is you can have a lot of distance between quantum states, but not always it corresponds to metricals in the sense of a metric space. Well, let's continue with this point. If you take the Euclidean metric, we work at this moment with the simplex space. If you took the Euclidean metrics, it can be written in this form, where the function g is given by this expression. Let's see this structure of the Euclidean distance between two arbitrary probability distribution. If you write the Jensen-Shannon, alternatively, it can be written in this form. Yeah, and if we compare the structure of the Euclidean metric with this expression, we found that they are similar. In some sense, that is the main point, the Jensen-Shannon divergence is a deformation of the Euclidean metrics. And they share two aspects very significant. The square root of this expression is a metric, and the square root of this expression also is a metric. So here appears the concept of deformation. Yeah. So we can think in something like a super operator that take Euclidean distance and modifying certain parameters, we can go through several other metrics. In one extreme is the Euclidean metrics, and the other extreme is the Jensen-Shannon metric. This idea was introduced by Bourbea and Rao in 1982, but we try here to give a different perspective or approach to this kind of divergence. Particularly, we want to extend this idea of deformation to the realm of quantum states. So we can introduce this family, this new family of divergence, by changing the function g. Let's recall that in the Euclidean case, g is the linear function, and in the case of Jensen-Shannon is the logarithmic function. So we can introduce a family of divergence by changing g whenever this product is a convex function. Well, if we require this property, it is easy to show that it's defined positive as symmetric, but in general, we cannot assure that the quantity square root of this divergence is a true metric. We will walk to this point later, okay? This is a very important point because we are searching for metrics in the sense that it satisfies the triangle inequality. It had been shown that the Jensen-Shannon divergence has been useful to analyze several problems in statistical physics and in quantum mechanics. For example, this divergence has been used to study time series, networks, multi-layer networks, quantum entanglement, and several other topics that makes this divergence a very significant one. Okay, there is a theorem, a classical theorem from harmonic analysis, known as the Hilbert theorem, that give a characterization that can be applied to indicate if this kind of divergence really its square root of the divergence is a true matrix, and the condition that it's required is that certain inequality be satisfied. In the previous definition, the characterization of the Schoenberg theorem required that this kernel, technically is known as a kernel, satisfies this inequality. Of course, this inequality depends of the function g. Yeah. This is an important aspect. Only we can assure that the square root of this divergence be a metric if this inequality is satisfied. It does not important the details, yeah, but only to mention that what is important in the definition of a new divergence. Another point is very significant. We have defined this new family of distance, and we want to compare with the Caesar divergence for two very close probability distribution. We can approximate the Caesar distance between P and P plus dP in this way. And for the divergence D sub G, we can approximate in this form. Whenever we assume that the G function be one differentiable. And here emerges a very important result, because the only dg, remember this expression, the only dg divergence, that is a Caesar divergence, is the Jensen-Shannon divergence. So we really have a new family of divergence, only coincident with the Caesar divergence in the case of Jensen-Shannon divergence. Okay, this is another important aspect of the this family of divergence. Another point of the Schoenberg theorem is that it, under certain conditions, it is possible to map the simplex of probability distribution into a Hilbert space. In order that this map allows to use the norm induced by the inner product in the Hilbert space and relate this quantity that is a property from the Hilbert space with the square root of the G divergence. Yeah, well, it may be difficult to find this map, but this is a very important result. There is a connection between the inner geometry of the Hilbert space with the Riemannian or the metric structure of the simplex P. Yeah. In some cases, it's possible to determine the function phi but in many other cases it's difficult to find this map. But this is a valid, general valid result, okay? Well, I don't know how I am the time. I suppose I have 10 minutes.
Yes,
so,
now you are on time. So now you enter the time for questions. So you can go on a little bit, but there will be less time for questions. Yes.
Okay, thank you, Federico. Okay, well, the other step in our work have to do with the extension of this classical divergence. I mean, by classical, the fact that we are evaluating this divergence between two probability distributions, and the question is how to extend to a distance between quantum states. Well, the natural extension of TG to the realm of quantum states is through this expression, where the function f is this product. We require, as before, that this product is a convex function, and here we operationally we have to evaluate the eigenvalue of rho, the eigenvalue of sigma, and the eigenvalue of the mixture. And from that eigenvalue, we can evaluate this tracer. Okay? There is a theorem. This is another very interesting result. When you do this extension to this classical divergence to quantum states, there is this theorem that affirms that the square root of this divergence is a true metric in the sense that it verifies the triangle inequality for the particular case of 2 by 2 density matrix. Yeah. In particular, as I said before, the Jensen-Shannon divergence is a particular case of this kind of divergence between mixed states. But recently, by two authors, one of these authors is Daniel Virostek, that in 2021 showed that the previous result for 2 times 2 matrix, and this other author in this year has made advances in the proof for dimension 3. And this author was able to prove that the Jensen-Shannon divergence is a true metric in the sense that its square root is a metric for any dimension. Yeah. So we have a proof that the square root of the Jensen-Shannon divergence between mixed states is a true metric for any dimension, and this kind of divergence is a true metric in the sense that it's a square root for dimension 3. For higher dimension is an open problem. Yeah, and we are working on this point. Okay, so in order to conclude, we have introduced this family of divergence between mixed quantum states, its square root is a true metric for dimension 3, and the general proof of the metric character of this divergence is still being an open problem. Okay, thank you very much. Any question or comments?
Okay. Thanks, Walter, for this wonderful talk. We are very happy that you are here speaking, because you were one of the professors that supported this conference from the very beginning. And if we are here, all of us here together discussing quantum theory is to a great extent thanks to you. So there is a question in the public about this. Professor Decio Krause asked, if do these quantum metrics obey the Hausdorff's property? In other words, can two systems always be discerned by open sets?
Yeah, in fact, I have to mention another important point. From a physical point of view, when you have a distance between, let me, for example, here, for example, when you have this kind of divergence between mixed state, you must require that, insist from a physical point of view, you must insist, we must require that this function be monotone, in the sense that if you apply a map, for example, a CP map to both states, you must obtain inequality between this quantity and the corresponding after you apply a CP map. For example, that has a very interesting interpretation, because from a quantum point of view, you can describe the evolution or the general operation of a quantum state from a CP map. The most general evolution is not given by the unitary evolution. So that property may be valid for some particular function f. It is difficult to prove that in general that property of monotonicity may be valid for any f. Anyway, we are working on that point, and we are trying to characterize for which kind of f function the monotonicity is valid. Yeah, I don't know if I answered the question, but the answer has to do with the study of that kind of property. Yeah.
Okay, so we are on time. Thanks, Walter. Decio Krause says thank you in the chat, so I think you
okay, but Prof, yeah, if he wants, Krause can write me and we can discuss that point longer. Okay.
Yes, perfect. I can give him your email. Okay. Perfect. Great.
Thank you,
so,
Federico.
Thanks, Walter. Thanks. So we are on time. So now